and off we go. If anybody has any questions during the live webinar, you are welcome to type them in the question chat box, and I'll do my best to pay attention to that and answer them as we go. So today's topic is part of the Friday controls series that we've been hosting. Last week was an introduction to DDC. Today is VAV. Next week is VVT. And then we added a fourth week on there, which is for the future of building automation systems. We've also done several other ones for CCN controls and things like that. We have a BACnet class coming up. It is 7 weeks long, in person, live in our Melrose Park building. We are back to having live classes, although we are limited to 8 students, so we can keep the student plus instructor headcount 10 and under. But if you're interested in learning how to program carrier BACnet systems, that class begins next week, and it meets 1 day per week for 7 weeks. In regards to VAV, variable air volume systems, there's lots of reasons why someone may or may not want a VAV system. The typical main reason for wanting VAV is that you want zoning. And what does that mean? That means you want more than one thermostat for your building or your office or whatever you have. You don't all want the exact same thing. You want individual control, and you're willing to do something about it. There are lots of ways to get individual control. For example, you could give everybody their own piece of equipment, right? So everybody could have their own rooftop unit, or everybody could have their own ductless mini split. Or you could do VRF, where everybody has their own indoor unit, but they share an outdoor unit. You could have fan coils with chilled water. You could have heat pumps around the building. But what we're going to focus on today is doing it with VAV, which means I'm going to have a single air handler, or in some cases in a big building you have multiple air handlers, but for a quote-unquote normal space, I'm going to have a single air handler with many different zone dampers attached to that. Now, there are more than one type of zone dampering system that you could have. We're going to talk about what we call VAV, variable air volume. There are other zone damper systems that are in the marketplace, such as VVT, and we'll talk about that next week, obviously, or a multi-zone system or something like that. But we're going to focus on VAV. So what exactly does that mean? All right, so what VAV is, let me see if my little laser pointer thing will work. So in this particular example, I have a VAV rooftop unit. It could also be an indoor air handler. That would be fine. It could even be a packaged vertical unit, something like that. But for us, it's going to be a rooftop unit, and we'll talk about how that rooftop unit needs to be set up and what features it needs, or air handler for that matter. But his job in life is going to be to provide cold 55-degree air down this duct system. That's pretty much his only job. There'll be some more jobs we'll give him as we go on, but his main job in life is to provide 55-degree cold air all the time, no matter what. No matter what means all year long. Even when it's negative 20 outside, this dude's job is to give me 55-degree air. Now, we'll tweak that sequence as this course develops here for some other ideas, but traditionally that's what VAV means, cooling all the time. So I got 55-degree cold air coming down this duct. Then each of the individual zones, in our example here we have 4 zones. Let me see, I got a question that popped up. Sorry, I'm trying to read the questions as they come in. From Chung, asking if we could add nomenclature in the system. I'm not sure what you mean by nomenclature, Chung. So yes, we can add it. Let me know what you mean specifically. Give me an example, and I'll make sure that we do that. So I got 55-degree air coming down the duct system. I have 4 zones in this particular example. So I have 4 rooms. Each one of those rooms has its own thermostat. And those thermostats are controlling what we're going to call a VAV damper. We'll define some of the different types of VAV dampers. But for right now, in your head, just picture it as a piece of sheet metal in the duct that opens and closes, letting more or less air in. It's basically a window in the duct system to allow airflow through or to block airflow. So those thermostats are going to decide how much cooling that room wants. There's no such thing as heating right now. We're talking about just cooling. The thermostat's can decide how much cooling it wants. So for example, if the thermostat is set for, let's say, 73 degrees cooling, and it's 75 degrees in this space down here on the right, that guy wants cooling. He will send a signal to the damper saying, I want more of that cold air that you have available, right? I have this cold 55-degree air, give me some more of that. Whereas maybe this zone over here is also set for 73, and it happens to be 73 in the room, he will throttle his damper back, saying, I don't need as much of that cold air, right? Giving me more or less of that. And those dampers are going to modulate between a minimum and a maximum position, which we'll define in a little bit here. But they're going to modulate to give me more or less of that cold air. And that's it. That's the whole VAV system. There's nothing else to talk about for a traditional VAV system. Now, we're going to talk about things that are not traditional. But right now, there's no heat in the air handler. There's no heat in the zones. Everybody wants cooling. Everybody wants cooling all year long. They just want more or less of it. Chun has clarified what he meant. He meant on this drawing that I screenshot here, it has 1, 2, 3, 4, 5, 6 on here. Asking to define what those things are, so we can go ahead and do that for sure. So starting, we'll just go numerically in order. Number 1 is the return air. So that's the air leaving the space. In this particular example, it's going to a plenum, an open plenum, but it could be ducted as well. That's a possibility. But that's the return air grill. Number 2 is the supply air and the supply air diffusers, distributing air into the rooms. Number 3 is the thermostat on the wall. Number 4 is the VAV terminal or the VAV box. Number 5 is the rooftop unit or the air handler. And number 6 is the duct system. Sorry about that, Sean. I didn't know what you meant when you said nomenclature, but now it's crystal clear. Thank you. So that's our basic VAV system. So why do people want this? All right, so first off, why do they want it? It's to be more comfortable. If I gave one thermostat for the building, only one of those spaces would be happy. Let's just say I put a thermostat in the president's office of the building. The president would get exactly what he wanted, but the other 40 occupants would get whatever he wanted, which may or may not be the right amount of cooling for their area of the building based on where the sun is at that moment. It might not be the right amount of cooling for their area of the building based on how many people are packed into that area. They would just get whatever the president's office wanted. So giving them that individual control for their individual rooms and spaces is going to be the comfort benefit. Everybody can have exactly what they want, assuming we do this right. Another benefit of a VAV system is load diversity. So what does that mean? You probably all have been on enough webinars of mine or classes to know that I always complain about things being oversized, because everything is oversized, like literally everything in our industry is oversized. But oversizing equipment is really detrimental on a VAV system. In fact, we're going to, I don't want to say undersize because that sounds bad. We're going to size the equipment smaller than we would if we didn't have VAV. So what do I mean by that? So on these zones here, you can imagine, in this case there's only 4 of them, but on a bigger project there might be 40 of them or 60 of them or whatever. But if I just have these 4 here, if 2 of them didn't want cooling and their dampers were shut, let's say they're all equally sized right now, and 2 of them were open, I would only need half the capacity of the air handler, right? So on a big enough system with 25, 30, 60 zones, the chance of every zone wanting 100% maximum cooling at the same time is basically 0. It's just not going to happen. So I can take credit for that, what we call a diversity credit or diversity factor, and I can size my system smaller. So for discussion purposes, it usually ends up being about 80%. So if I needed a 50-ton air handler, right, that's how big the air handling system was that I was going to put in. Now I'm only going to put a 40-ton air handler in instead of putting the 50 in. I'm going to bank on the fact that all the zones are not fully open at the same time. They may be partially open at the same time. 2 or 3 may be fully open while a bunch of other ones are partially open. But the chance of every single space being open, 100%, which means that somehow the sun is magically shining on both the east and west sides of the building at the exact same moment, and every single person is showed up to the building. I'm going to bank on the fact that that doesn't happen and size the equipment smaller. Now, I made up the 80% number just as a rough discussion. It could be 65%. It could be 90%. The way you're really going to figure out the diversity factor is when you look at the room-by-room load calculations that you're doing for the building, which you need to do in order to size the duct system. You're going to look at that and look at when their peaks are to determine the actual size of the equipment I need to see when the coincident largest peak of the most amount of zones happens to be, and then that's the tonnage I'm going to size for. There's going to be an energy saving benefit. Part of that's coming from the compression side of the equation, being able to stage things down. But honestly, the big energy savings on VAV, in fact, almost all of the energy savings, if you will, comes from the fan system and being able to throttle that fan back. And we'll talk about that in detail and how we control that fan and where the energy savings comes from specifically. But the fan energy savings is going to be pretty impressive on a VAV system, and that makes it an attractive system for a lot of buildings. Design flexibility is another thing that we hear a lot. So what do I mean by that? If I was to have like a tenant finish out space, let's say I did a core and shell building. I built this building, whatever it is, 6 stories. and my job is to build the core and the shell, right? Which means I build the interior of the building, the bathrooms, stairwells, etc., and the outside walls, and I give you your air handling system, but I don't handle any of the ductwork on any of the floors or the thermostats. None of that's my problem. If I was to do that with regular constant volume equipment, I would need to know where I wanted each of these things to be inducted to. With VAV systems, what I can do is build that core and have like a loop going around each floor for the duct system. And then as the tenants build out their area of the building, they could tap into that duct system and pull their air from pretty much anywhere on the duct loop. And then if somebody moves to a different area or different zone, then you're going to say, you know what, we're going to make this area a copy room. We need more cooling. I could put another duct run in there and take it away from something else or something like that. Whereas if I did something with, say, ductless mini splits or VRF or chilled water, fan coils, going to each one of those zones, it makes it really hard to move. Not that you can't move those things, it's just way easier to move ductwork than it is water or refrigerant systems, because those systems need to be completely drained back on the water or charge taken out on the refrigerant side in order to add and subtract piping. Whereas with air, I could just move it. I don't have to worry about anything leaking out when I move it. And then I also have the ability to only control some parts of the building and not others. I can make some zones be occupied while others are unoccupied. And because of the staging capacity on VAV, which we'll talk about, I can handle that. There are disadvantages. There are times that VAV may not be the best fit for your application. For example, I may have an existing heating only building that I'm gonna some heating only building, I'm gonna turn into some loft offices or something like that, and now I need to add cooling. There may not be a lot of space to add ductwork, to add cooling, right? If I had a heating only hydronic system with baseboard or steam radiators, I'm kind of in trouble there. I don't have ductwork or space to put it, so maybe a VRF system might be a good spot for that, whereas VAV might not be the best, because I don't want to drop the ceiling height to make room for all this ductwork. So there can be times where VAV would be at a disadvantage. The other place that VAV has historically struggled, but is getting better at, is on really small systems. Because I have a system that, by definition, provides 55-degree cold air year-round, that makes it very hard to do with a small system that needs a lot of heating on the perimeter. There are better ways to do that than with VAV, and we'll talk about some of those. Any other questions as we're going along here? So here's where I was going to lay out the various components. To Chun's point earlier, it's not the exact same drawing we had earlier, but it's very similar. But we'll walk through this one as well. So number one on the drawing is my VAV rooftop unit, or it could be a VAV air handler inside the building if I prefer to do it that way, or other types of VAV equipment. But it does need to be equipment that is specifically designed and set up to be VAV. A regular rooftop or a regular air handler is not going to do a good job of being bastardized into a VAV system. I'm not saying you couldn't do it, it's just not going to work well. You want to get a piece of equipment that's been designed for that. Specifically, what we mean by design for that is it needs to have a certain requirement for ability to control airflow and a certain requirement for the ability to control discharge, air temperature. And we'll talk about how to do both of those things. So I got a VAV air handler, a rooftop. Number two on the drawing is my VAV terminals. And that could be a VAV box, which is, like I said before, basically a sheet metal damper. We'll go through all the different types of terminals. Or it could be a one that has a fan assisted ability to it. And we'll define how that works as well. My supply air and supply air grills. Now, the diffusers that I'm going to use for supply air also need to be specific for VAV. Just like the air handler can't be a regular constant volume air handler, well, the diffuser can't be a regular constant volume diffuser. I need to have one that has good ADPI, good throw characteristics to it. If not, when I throttle the airflow back to that zone, I throttle the CFM back. If I have a crappy constant volume diffuser, it's going to dump the air straight downward. And I still want the air to be thrown out to the sides, left, right, front, and back in my drawing. And I need to have a diffuser that has the ability to throw the air at low turn down levels. So you need to buy one that specifically is designed for VAV systems. Do not put a regular constant volume diffuser on a VAV system, or you're going to get dumping, which means whoever's desk is sitting right here is going to probably complain. I'm going to have additional control wiring that I would not have on another system, because I'm going to have a thermostat and a on each wall and a controller at each terminal and the wiring in between them. Whereas on a regular constant volume system, I would just have one thermostat for the whole entire rooftop unit. So now I'm going to have more wiring involved that I have to do to control this. I may also have control wiring that networks these terminals together, as well as networks the rooftop in, to tie those into a building automation system like we talked about last week. I'm going to have my return air grills. Hopefully they're not like this drawing where the return grill is right next to the supply grill, because I'm going to get some short cycling there. But I'm going to have return grills for each space to bring the air back out. I can't put air into a room if I don't take air back out, obviously. I'm going to have the thermostats for the zone. And if you notice, at least at the moment, I do not have any thermostats on the air handler or rooftop. The air handler rooftop does not care at all about what the space temperature is. That is not his problem in life. Doesn't care. You get cold air no matter what. I don't care. The thermostat just modulates how much you get at each zone, but the air handler just runs cooling all the time. So there will not be a thermostat in this space for the rooftop or the air handler. Now there could be, but that would be a unique thing. Maybe you might put a thermostat in there and wire it into the controls of the rooftop or the air handler to only be used perhaps at night. When the system is off, you might be able to bring on, in this case, the gas-fired rooftop unit to provide some nighttime heating. And that can be done with a regular thermostat, in addition to the thermostats we have on the wall here. That's not very common because nowadays most of these VAV systems are DDC controlled, meaning all these boxes are networked together. So instead of throwing another thermostat on the wall that's hardwired to the rooftop for nighttime heating, we would just look at all the thermostats that are already in the space on the building automation system. And if those guys as a group started getting cold, we might do some nighttime heating. So you would have to install any extra stats. The supply fan is going to need a VFD on it or some other type of airflow and static pressure control. And we'll talk about the different types that could be existing, but VFD is going to be 99% of the scenarios that you're going to have these days. So you're going to have a VFD on there to control the speeds of the fan. It's important to note that this VFD needs to be a modulating controlled VFD on static pressure in the duct system, which is where number 8 is on here, my duct static pressure sensor. He's going to be doing that control mechanism for me. You could have a VFD on a rooftop or air handler that is set up for what we call staged air volume, and that would be a 2-speed fan. So it might have a VFD on it, and a lot of rooftops have a VFD now. In fact, all the rooftops we do above like 6 tons for code compliance, we got a VFD on them in Illinois. So you're going to see a lot of VFDs on rooftops, but that does not mean it's a VAV unit. Those are 2-speed VFDs. The VFD only runs at 2 different airflows, 67% and 100%. That will not work on a VAV system. I have to have full modulating control and a static pressure sensor down in the duct system. The location of this duct static pressure sensor, where number 8 is at here, this guy cannot be over here at the discharge of the fan. He cannot be here at the fan section of the air handler. He needs to be down in the duct system. He needs to be in the trenches so he can experience what these zones are experiencing. Ideally, in the perfect world, what you would do is you would look at your duct system and you would say, okay, I have all these 30 zones on here. Which zone is the quote unquote farthest? I say quote unquote for farthest because I don't want to know which one is geographically the farthest or even linearly the farthest. I want to know which one has the highest static pressure drop duct run. Now, it's usually going to be one of the farthest zones, right? The further you get away, the more static pressure you have. So that farthest zone at the end of the building is going to be one of the candidates for being that one. But there could be a closer one. It could be this zone number 10. Instead of zone 30 at the end, it could be zone number 10 here. Maybe he's got some really jacked up duct run that has like 17 elbows in it for no reason, right? In those cases, then maybe it would be something closer. But usually it's going to be the farthest one. We look at the duct static pressure for that farthest zone. And if he's getting enough pressure in order to get the CFM that he needs, then everybody upstream must be getting enough also. That would be the perfect scenario. That's very difficult for you to figure out where to put until the building's actually built. So normally what we do is we put that duct static pressure about 2/3 of the way down the duct. How we got the 2/3 number? It's just a wild ass guess, right? It's just a decent educated guess. The current codes no longer allow us to put it 2/3 down the duct. We'll explain later on at the end of today's presentation what the current codes make us do. But for right now, we'll go with the traditional scenario, which is putting it 2/3 down the duct. If you put the static pressure sensor in the fan here or in the discharge of the rooftop unit, then what will happen is that the VFD will back off very little. It won't have much ramping ability because what's happening downstream with these dampers won't really be perceived by this static pressure sensor over here. So that's not going to do me much for ramping the fan down. If you are a service guy or gal and you go to one of these existing buildings that has a system and you see the VFD is running at 100%, all VFDs in all buildings for pretty much all reasons that are running at 100% are probably not working correctly. Something's broken, something was never configured correctly, or somebody in the building put it in manual mode just to get some airflow going. 100% would be rare. That means you're at a design day for weather and a design day for occupancy. So that hardly ever happens. So whenever, as a controls person, you see 100% on the VFD, it's a red flag that something's probably not right. Normally, you're going to see things operating 40, 50, 60%. It's kind of the normal range of a day-to-day operating VAV system. Catherine has a question. Actually, Catherine does not have a question. She's making fun of me because I mentioned, so I called something a boy, apparently. Everything in this drawing is gender neutral. It is not a boy or a girl. It's all gender neutral from now on. I'll try to be more politically correct. Where do we leave off? That was 8. Number 9 is my supply duct system. And then obviously I have return duct as well. Now this building in my drawing does not have a return duct. It's got an open plenum, which means the return air goes up into the ceiling above the acoustical ceiling tiles, and then it makes its way into a very short return grill. But you could duct the return to each one of these grills and do it that way if you would prefer. And that choice we made external to the VAV choice. Both VAV and constant volume systems can pick and choose between ducted returns and plenum returns. VAV tends to have plenum returns because it allows the fan-powered boxes, which we'll talk about later, to do their job better. So plenum returns are very common on a VAV system. If I look a little bit more at the air handler itself, or the rooftop, depending on which way you're doing it, we mentioned that we had to have a VFD on there or some type of fan control. It's going to be a VFD, but that we have to have that on there. We also need to have a few other things. For example, the evaporator coil, we'd prefer to have a evaporator coil that is full face active, meaning I don't want a split coil where compressor number 1 handles the top half and compressor number 2 handles the bottom half, because then I get a lot of bypass air. That's not the worst thing in the world for some constant volume systems, but on a VAV system where I'm running at part load a lot, but I also need to do part load capacity even on hot, humid days, I want to have this full coil active so I have a better ability to get down to the dew point at those lower airflow scenarios, even though I might still need the low dew point temperature. So when you get a VAV air handler or fan or rooftop unit, it's going to have a full faced coil on there. So this only is going to be something you got to pay attention to if you're retrofitting, converting something to VAV. I'm going to need to have the ability to measure supply air temperature. I'm going to be controlling to provide 55-degree air all the time. So if I'm doing that, I have to measure it. Otherwise, I can't do it. So I got to have a supplier temperature sensor. It's usually going to be mounted on the inlet of the fan because most of the time the fan is a draw through, meaning it's pulling through the evaporator coil. And if I put it right at the coil, I'm going to get a little bit, I could have some inaccurate readings. I want to be a little further downstream once the air is a little bit fully mixed. So putting it over towards the evaporator fan is typically what's done. I could also put it down here in the supply duct if I chose to. Usually on a rooftop unit, it has packaged controls already on it, meaning the sensor's also wired already. So it's pretty much already going to be in here for you. On an air handler, the controls are typically field installed by a building automation contractor, and then you're more likely to find the sensor in the duct system. But either way would work. One caveat to point out is on a rooftop unit, if you have gas heat, which is very common for us here in the Midwest, the gas heat is typically after the fan on most rooftop units. So when you see the supplier temperature sensor, it's downstream of the cooling coil, but it's actually upstream of the heat. Why does that matter? It only matters because sometimes when it goes into morning warm up and it's actually running the gas heat, you'll look at the supplier temperature sensor and be like, dude, why is it like 60 degrees? What the heck's going on? This heat's full blast. It's 60 degrees because it's upstream of the heater. So your building automation system can't tell you what the discharge air temperature is on the heater unless you add some supplemental sensors in the duct system. And then the last thing we have is a return air temperature sensor. This is not always required, but if you do not have DDC controls, then you're going to have this. And it's probably going to already be factory installed on the rooftop because it's just a thermistor. It's inexpensive. It's easy to do. So it's already going to be in there. That guy's main job in life is to tell morning warm up when to stop. So I mentioned before, we provide 55-degree cold air down the duct all the time, 24/7, 365, no matter what, and heating's not our problem. The exception to that, well, there's going to be multiple exceptions as we discuss things, but the major exception to that is what's called morning warm up. So the premise of a VAV system is that it's in a cooling dominated building. Otherwise, you wouldn't be buying a system like this, right? If you don't have a cooling dominant building, you shouldn't have a system that provides cooling all day. It's in a cooling dominated building, but in the morning, before the building goes occupied, it's been cooler at night, the lights are off, the computers are not on, the tenants are not in there yet, the building is a little bit cooler. So what we do is this cycle called morning warm up, where we blast the gas heat on in the unit, and we warm the space up before the occupancy period begins. And then when we go occupied, we go to cooling. So let's say the building's going to go occupied at 7:30 a.m. Well, at 6:30 a.m., we may turn the morning warm up on and heat the building until the return air temperature gets up to some predefined point, say maybe 68 degrees. And once it's 68 degrees, we shut the morning warm up off and we go into the cooling mode for the rest of the day. And we never bring the heat back on at all. If somebody needs heat in their space, we'll handle that with their local zone heat, which we'll talk about later on. All right, it is time for our first quiz question. So let me come over here. For those of you that need PDHs, you have to answer the quiz questions and answer them correctly. For those of you that don't need PDHs, you can just do it for the pure fun of it. So question number 1, what is the typical discharge air temp of a VAV system? 50 degrees, 53 degrees, 55 degrees, or 57? If you are not able to click on the answer in the poll, it may be because you're in full screen view. So you may have to, on your GoToWebinar view, just go back, click on it, or hit escape so you don't go to full screen view, and then you'll be able to click on the poll questions. While you guys are answering that, I'm going to read a couple other questions that came up. Ferris asks, can a system have a combination set up between VAV boxes and regular ductwork with normal registers and outlets? Yes, you could do that. It would not be advisable, but it could be done. So what he's saying is that he wants to have a couple zones that are essentially wild, and they don't have any dampers to throttle the air back. You could do that, but the problem with those scenarios is that those zones are going to get 100% airflow of 55-degree air all hour long, all occupied hours of the day. So the only place you might be able to get away with something like that is some place that needs a crap load of cooling. So maybe like a server room or something like that might be able to do it. But even then, we typically don't do that. We typically put the VAV box on there anyway, because if I'm going to buy 60 VAV boxes, I might as well buy 61 VAV boxes and just have some control over the server room if I need it. But it would have to be an area of the building that wants a lot of cooling all the time, no matter what, nonstop, all day long. So you probably wouldn't want to do that. All right, hopefully everybody was able to answer the poll questions. I'm going to close that in 5 seconds. 4, 3, 2, 1. And it looks like 96% of you guys got that correct, saying that it is 55-degree supply air is the typical discharge air temperature of a VAV system. Let me hide that and go back to the slides. All right, so when we're laying this space out, there's some things we're going to have to consider. We're going to try to get this done with one air handler. Let me go back to my laser pointer thing. Get this done with one air handler, or at least one air handler per floor. Now, normally, if I don't have VAV, if I have constant volume systems, meaning rooftops, air handlers, fan coils, things like that, in those applications, we do not want you to use one rooftop unit or one unit for the whole entire building or the whole floor even. Because the problem is going to be is that the east side of the building is going to have sun in the morning, the west is going to have it in the afternoon, the south is going to have it the whole middle of the day, the interior is never going to see the outdoor temperature at all affecting it, right? So the problem with having one system like that for constant volume is that I can't make everybody happy on all sides of the building at the same time. But once I have VAV and I have the ability to throttle the zones back, I can do that. So how am I going to lay out these zones? Well, here's what we need to do at a minimum to do it right. Now, doing it and doing it right are going to be two different things, but this is what we need at a minimum. We need at least one zone meaning a VAV box and a thermostat, for each unique space that needs different temperature things. So from a exposure standpoint, from a perimeter standpoint of the building, that's going to equate to me having 8 different zones. I'm going to have an east and a west and a north and a south. And then I have the 4 corners that go along with that, because each corner is kind of a combo of things, right? So this corner down here is going to have sun in the morning from the east side exposure. So he's kind of this guy's buddy. But then later on at 10 o'clock in the afternoon or 10 o'clock in the morning, he's no longer similar to this guy's needs. He's getting the sun beat on him like these guys are down here. So these guys are kind of buddies, right? And then later on over here, right? And the north never gets any direct sunlight. So if I had those 8 around the perimeter, that would handle all my unique exposures. And then I have the interior area, which doesn't have any exposure. He never sees the sun unless it's the top floor of the building and he's got a bunch of skylights or something. But other than that, he never sees the sun. So he never has that effect on him whatsoever. And he never has any thermal heat loss or gain through the walls. So he's going to be unique from all the perimeters. So 9 zones is what I would need to do. I'm not yet considering how the space is used. That'll change some answers too. Or how big the space is. That might change some answers. But just from a general discussion, 9 zones. Now, I may compromise and combine some things. Like this guy up here in the northeast corner, I may choose to combine him with the north. Yeah, he's going to get some sun in the morning. Maybe I'm not super concerned about it. Maybe I can just deal with that for an hour or 2 before the sun moves around. Not a big deal. And maybe I had the same feeling about this guy over here. I could start combining zones to save cost if I wanted to. 1 less VAV controller, 1 less thermostat, that kind of idea. But when I do that, I have to know in my head each time I'm making a compromise, right? Oh, I'm going to combine this guy over here with the rest of the north zones. Okay, fine. When I do that, I just have to know there's going to be a couple hours each morning that that person is not as comfortable as they otherwise would be, and they might complain about it. And depending on how important that person is, may affect my decision. Now, that room could be something else. It could be a storage room. Okay, well, if it's a storage room, then I really don't care that much, and I would go ahead and combine them with somebody else. If it's a private office, I probably would care. This big interior zone, I don't have any dimensions on this drawing, but if this was a really, really, really large space, maybe instead of one big zone with 5,000 CFM, maybe I would want to divide it up and have, 3 or 4 zones taking care of that. One of these spaces might be a conference room, right? Maybe there's a conference room that's literally right here, right? So if I put a conference room in there, I no longer want that conference room in this area right here to be grouped in with the rest of this zone. Because that conference room at any given time could have 0 people in it, or it could have 15. So that guy is going to be a unique space, and I'm going to want to have him be controlled separately. Ferris asked a question. In general, how hard is it to balance the airflow for a system outlets having VAV boxes? The balancing is not hard, and any decent air balancer would be able to do it, because VAV systems are actually really, really old. This is technology from the 1960s. Yeah, we made it better with DDC controls and some modern stuff. But generally speaking, this has been going on since the 60s. So the ability or the knowledge needed to balance these systems is not proprietary by any means. Any commercial air balancer should be able to balance these systems. Now, it is significantly more difficult than a constant volume system, especially if I have diversity going on, right? If I've only sized it for 80% of the airflow, well, now it's really hard. I can't balance it at 100% and get enough airflow to all my zones. So I got to kind of divide things up in chunks when I'm doing the balancing. But I need to balance the VAV boxes and the diffusers. The VAV boxes have multiple steps to balancing them. For starters, I have to calibrate the sensors on the VAV boxes. We haven't gotten to that point yet, but we will. The VAV boxes have inlet sensors on them to measure pressures and calculate the CFM. So the VAV box knows at all times how much CFM is running through it. And those sensors need to be calibrated. So usually it's the air balancer and the controls guy working together to do that. The controls guy has the software and the ability to access those sensors, and the air balancer has the expertise and the really good tools to measure things correctly and then help us calibrate those sensors. Then once those things are calibrated, we need to set up the airflow limits on the VAV box. There's going to be minimums and maximums on those boxes to tell me how much air I should be moving, right? So for example, I may have a zone that is 1,000 CFM on design day, and I may set it up for 200 CFM minimum airflow to get my ventilation air. So now someone has to go into that controller and say 200 and 1,000 are the mins and maxes, and then the box can modulate in between those two as space temperature demands. And then, of course, you have to still balance the fan on the air handler itself. You have to balance the return side. You have to balance the outside air economizer or minimum ventilation position, on there that you would have to do as well. So there's going to be a lot of steps on there. Some of them you have to do on a constant volume system. Some of them are unique to VAV. But balancing is actually a pretty big deal on these systems. Actually, it's a pretty big deal on all systems and something that we can all probably improve upon. Here's a really small office area that we can use as an example. So in this case, we have a packaged rooftop unit doing our VAV control. We have 1, 2, 3, 4, 5, 6, 7, 8 dampers on here. We've made some of the compromises that I just mentioned. So for starters, the first thing to look at is where we put the rooftop unit. We put it above the bathrooms. That is ideal. In general, I would always rather have the equipment be above, what's the best way to think of it? Above non-office spaces, right? If you have equipment that happens to be loud or anything like that, you don't want that above the conference room, right? So putting things above the bathroom tends to get little objections and complaints related to them for noise and stuff like that. We chose to put it there. Now, this particular building, this is an office that was attached to a manufacturing facility on this side over here on the north side of the building, right? So this side, this wall here doesn't really have any north exposure for the most part, right? It's got a 50-degree warehouse next to it. But over here, you'll look on the zones on the right-hand side. We have one zone over here that was serving a conference room. We have another zone over here serving a private office. That's the main reason why we split those two things up. It's because you never want to put a conference room on the same thermostat as the office space, right? No matter which place you put the thermostat in, it's going to cause complaints in the other space, especially when there's 10 people in the conference room. We got a corner office. He got his own thermostat because he's got exposure to both zones. We have one zone handling the whole front end of the office on the south side here, and there's his thermostat. We have another zone over here handling the other corner because he is exposed to both the south and the west. And then we have one thermostat handling this whole area over here. Now, let's say over here on the left-hand side, where I have my red cursor over here, let's say instead of one big open area, let's say that was 5 unique offices. Each one of these diffusers was an office, and there was partition walls between each of these. The best thing to do in that scenario from a comfort standpoint would be to give all 5 of those offices their own thermostat and their own damper. Then they could all have their own individual temperature control. That would be the best thing from a comfort standpoint. It obviously would be not good from a first cost standpoint because now I got to buy 5 sets of controls instead of buying only 1 set of control for that area of the building. So what ends up happening, even if these are divided offices, in practice, what ends up happening is these zones often get combined. Someone will say, you know what, we're not doing that. We're not buying 5 of those. We got to get things under budget in this project. So we're gonna do 2. These 2 zones are gonna be grouped together, and then these 3 are gonna be grouped together. Or they may say we're gonna do 5, and they're all grouped together. Somebody's gonna make a decision on making those compromises. But from a comfort standpoint, every unique space that has its own walls should get its own damper and its own thermostat. But you'll compromise and you'll choose not to do that in some cases. Then we have 2 zones taking care of the interior. We could have did it with 1, but a lot of times, like I said, you might divide it up, get a little bit more individualized control. So I have 2 dampers in this case. In this case, they're actually controlled off of 1 thermostat, so there isn't going to be any individual control. It was just easier from a ducting standpoint, the way this was laid out, to have 1 damper going to the left, 1 damper going to the right. Personally, if it's me and I bought this and I'm going to pay for 2 dampers and I'm going to pay for 2 actuators and I'm going to pay for 2 controllers on there, I might as well pay for another thermostat and put that thermostat over here somewhere and let this guy have slightly different temperature control than this guy. But you can combine them. You can gain 2 dampers off of 1 if you wanted to. The other thing I'll point out on this drawing is that some of these dampers have a little black box on the end of them. And then the 2 in the middle don't have a black box. For this particular drawing, that little black box meant a supplemental duct heater. In our climate here in the Midwest, even though I have a building that's cooling dominated, and even though my air handler is going to run cooling all the time, my perimeter zones that have all this glass window exposure, those guys are going to need heat at some points of the year. So instead of putting the air handler into heating mode, each zone can have its own heater. Now we're showing duct heaters on here. but it could also be baseboard heaters. Baseboard is actually a little bit more comfortable. The whole idea of washing the window with the warm air, basically putting the heat at the point where the cold problem happens to be, which is the window. But I could have baseboard electric or baseboard hot water, or I could have ducted electric or ducted hot water. Any one of those would be acceptable depending on what I'm trying to do with the rest of my building and whether I already have a boiler for other reasons. This one happens to be duct heaters on here. And in this case, it happened to be electric, but it could have been hot water just as well. Now, the two interior zones don't have the heaters. Why don't the interior zones get a heater? Well, because interior zones don't need heat at all, ever. Unless you have some kind of freakish amount of outside air, you don't need to heat the interior of the zone. Well, why not? Well, you don't need to heat it because over here in zone number 4 down here, it's a 72-degree room bordering this guy. And over here in zone number 6, it's a 72-degree room bordering this guy. And over here, it's 72. And over here, it's 72. And the floor above them, it's 72. And the floor below them, it's 72. Well, if I'm a 6-sided cube and it's 72 degrees on all 6 sides of my cube, why would I be losing any of my heat? I don't need any heat. I'm already surrounded by warmness, if you will. So we don't put heat on interior zones on a VAV system. Actually, we don't put heat on interior zones at all, or we shouldn't be putting heat on interior zones. The only time you would need heat is if you're going to have a really, really high amount of outside air. You may need some heat for a little bit of tempering just to get it back up to basically 55 degrees. But other than that, you don't need heat on interior zones. That's also one of the reasons why we can't have the air handler provide my heating for me. It does a little bit of morning warm-up, but then remember, it's done for the day, and it's cooling only the rest of the day. Because if I was to allow this guy to go into heating mode, because maybe these guys over here in the morning need some heat or whatever, how are the guys in the middle going to get their cooling now? There's 100-degree air in the duct. How am I getting cooling for these guys in the middle that need cooling year-round all the time, no matter what? Because an interior zone needs cooling on a 0-degree day. An interior zone needs cooling on a minus 20-degree day. So I need to have that cold air available for those guys at all times. So that makes it really hard for me to ping-pong the unit back and forth between heating and cooling. So another reason why we end up with cooling-only air handling systems. All right, quiz question number 2. And I mentioned this twice, so we should be able to get this, right? When does the heat normally run for a VAV air handling unit? Your choices are when the thermostat requests heat, in the morning before the building is occupied, in the winter time, or there is no heat. So on a normal VAV air handler, when am I going to energize that gas air handler heat, or that electric heater, or that hot water coil? All right, let's see if we have any questions for me while you guys are looking at that one. All right, Chun asks, should one thermostat pair with one volume damper? The answer to that is yes. A normal scenario would be a 1-to-1 relationship between thermostats and dampers, because you're going to select the zones you want to uniquely control, so that those guys are all going to get a thermostat, and then you're going to usually be smart about your duct work, so you can have one duct running to that zone, and hence one damper. So typically it's a 1-to-1 relationship of thermostats and dampers. However, as you saw in my previous drawing, I had one thermostat on 2 dampers for the interior zone, and that's allowable and sometimes does occur, and that's maybe because it was easier from a ducting standpoint. And maybe it was easier depending on the size of the dampers. Maybe putting 2 small dampers in from a ceiling height perspective was easier than one giant damper. The other time you may do it is if you have existing ductwork. Maybe I have an interior zone that has 4 duct runs coming off the main branch going to it. Or maybe I have a conference room that has 2 duct runs coming off the main branch to it. It may, in some cases, depending on how accessible the ductwork is, be easier to put 2 dampers in with one thermostat than it is to redo the ductwork to have only one larger branch run running to that zone. So normally 1-to-1, but you can do it a little bit different. All right, I'm going to close the poll question in 5, 4, 3, 2, and 75% of you guys got that correct, which is the normal scenario is that the morning warm-up period before it goes occupied is the only time that the heat would run on the VAV air handler. Ben asks, could C also be an answer? If you are bringing in minimum OA and you don't have adequate return air to temper to 55. So for a normal VAV system, there is no ability to temper the air back up to 55. Now, we could build it that way, and we do. So, for example, obviously we do carrier equipment at TEC here. We have carrier VAV rooftop units that have the ability to do tempering, and we have other ones that don't have the ability to do tempering. You could buy it either way. The ones that have tempering are the ones where we have an accessory called staged gas heat, or sometimes referred to as modulating gas heat. And those will have stainless steel burners in them, so we can have the ability to throttle the gas heat back without having to worry about condensation and corrosion on that guy. So in those cases, we could buy a rooftop unit with staged gas heat, and we do what's called tempering mode, and we put some extra sensors in the duct system so we could temper the air back up to 55 degrees like Ben is describing. I could also do the same thing with an air handler that had a hot water valve if I wanted to. I could add that sequencing in. But a normal traditional VAV system would not have any ability to temper the air back to 55. So Ben does have a good point. If I have a very high amount of outside air requirements for my space, I'm going to want to think about designing it to have a tempering mode like that, which means my air handler supplier or my rooftop supplier may need to order something different for me, and then my controls contractor will need to program something different for me. But if you just say VAV out of the box, you're not going to have any type of heating up to 55. And by the way, the tempering, like Ben was asking about, back up to 55 degrees, is still a cooling mode from the perspective of the system. We're still providing 55-degree cooling air to all the spaces. We just happen to be heating it to get 55, because if we didn't, maybe we'd only have 49 or something like that. So the system would still be in a cooling mode, but the air handler might temper the heat back up in that scenario. It's a really good question, Ben. Chun asks, does it apply to constant volume systems? Does what apply to constant volume systems? Are you talking about the modulating or staged gas heat? You could do that in a constant volume system if that's what you're asking, Chun. It's not as common, but you definitely could do that. In that case, on a constant volume system, though, you would not have discharge air control, so it wouldn't really work the same way. But you could put that modulating heat on those if you wanted to, and then the controller in the system would control it a little differently. So on a rooftop unit, we'd add sensors to the DDC controller that comes factory installed on the rooftop, and he can be told to do a tempering mode. On an air handling system, from a building automation standpoint, we would wait for the thermostat to call for heating, and then when it in fact called for heating, we would then modulate the heat to get me back up to whatever I wanted. I can have staged air control that way or modulating control that way. All right, from a static pressure standpoint and an airflow standpoint. So I have this duct system providing me this cold air all the time. And then I have these dampers that are going to throttle back in the duct in each individual zone to give me less of that cold air. So when those dampers throttle back, the static pressure in the duct system is going to build up because they have too much airflow for the amount that I want to use. If I got a zone that normally can move 1,000 CFM and he throttles back to 350 CFM, that means I got to cut back the air handler 650 CFM. The way we're going to do that is by measuring that static pressure in the duct, and as the dampers close back, modulate back, the static pressure will build, and then we will do something at the air handling system to reduce that static pressure. There's several ways we can do that. I previously mentioned the VFD, and that's obviously the most current way, but traditionally we did what was called inlet guide vanes. So this is the fan housing here, right? So my airflow's being sucked in through here. It's centrifugal fan, so it whips around and exits out the side over here. So these inlet guide vanes, that's these little dampers that are on here. And those guys modulate more open and more closed. So as the static pressure in the system builds, these little dampers choke it down at the inlet of the fan, so we don't even send as much airflow and static out to the system, if you will. This is the way VAV was done in the 60s and 70s, and even into the 80s and sometimes 90s. We did it with inlet guide vanes. And then at some point in the early 90s, VFDs had become more popular. They had become more reliable. Their cost had become a little bit lower, and that made it more feasible for the industry to start using VFDs instead of inlet guide vanes. And now we're at the point where VFDs are standard for all VAV systems. You could have done discharge dampers. So instead of having dampers over here on the inlet of the fan, you could put a discharge damper on the outlet of the fan. I've never actually seen anybody do this, but I figured I'd throw the drawing in here. One, just because it's in all the VAV manuals, so I figured, hey, I might as well show you what it is. And two, one day I'm going to meet one of you guys that's actually seen one of these systems, and you're going to tell me about it. So if you've ever seen this, let me know. I want to hear from you how well it worked. But theoretically, this would work. You could put dampers on the discharge of the fan instead of on the inlet of the fan, and modulate the airflow back that way. You see the note on here: forward curved fans only. They didn't want it on the backward inclined fans because, for whatever reason, they generate a lot more static than a forward curved fan, and it was too much for these dampers to really handle. You could also do a VFD, obviously, and that's the way we're going to do it nowadays for the reasons that I had just mentioned. So what's a VFD going to do? We don't have an hour to go through VFDs. That's a separate class, which, by the way, we do have recorded, and you can check it out on our website if you want to. But the 30-second version here, a VFD is going to take AC power in. It's going to convert it to DC for the purpose of my microprocessor being able to manipulate the signal easily. And then it's going to spit it back out AC to my motor. It's going to actually change the frequency of the waves, though. So I would have a sine wave, right, for all my electrical power. My AC power has a sine wave. We'll look at that artistic skill. I am mad artistic, right? And then what I'm going to do is I'm going to reduce that frequency. So frequency means from one peak to the other peak, or it could be a valley to the valley, either way, whatever way you want to think about it. How many of these peaks would go through the electrical system per second? So a normal system is 60 hertz, which means I would have 60 cycles per second. My VFD is going to change that. And instead of 60, it's going to give me 48 or 32 or 41 or 59 or something like that. He's going to change how many of these peaks will pass through per second to change my hertz. So if I'm going to have it run at 48 hertz instead of 60 hertz, that is going to equate to my fan actually providing me a slower airflow and less capacity. Let me clear that so I can keep going on my slide here. Fan systems are oversized like everything else. If you've been at any of my classes or webinars, you know I've complained about chillers, cooling towers, boilers, heat pumps, geothermal systems, VRF systems, residential splits, furnaces, boilers, everything being oversized. And guess what? Fans are no exception to that. Fans are oversized as well. And it's not just me saying it. I've actually went out and found some data. A Johns Hopkins study references that the average building has fans that are oversized by 60%. That means there's somebody who's only oversized 10% and somebody else is 200% sized in order for me to get an average of 60. But in any case, oversized. And VFDs have a very good dollar operating standpoint, much more so than the old Inlet guide vanes, which is one of the reasons why we were able to switch to this pretty painlessly. If you have a VFD on a regular fan running, or a regular fan without a VFD, running at full airflow, and let's say it costs you $1,000 a month to run, this is obviously a big fan in this case. If you cut the airflow down to 75%, it only costs you $420. Now your customer is thinking it's going to cost $750, right? Well, it cost me $1,000. If I cut it 25%, it costs me $750, and they might get excited about that, but they'll get really excited when you tell them it's only going to be $400, right? And if they cut their airflow in half, it's down to $125 a month, right? This is due to the fan laws, or I'm calling the affinity laws on here, just in case there's a pump guy. The pump guys call it the pump laws. The fan guys call it the fan laws. Generically, we call it the affinity laws. And we'll explain the affinity laws that apply to our situation here in a minute. We'll talk about why it works. In addition to the energy savings and getting us the airflow we need and quieter sound when it throttles back, the other benefit of having a VFD on my fan is that it means less wear and tear. Normally, when I turn an AC or an inductive type load on, I turn an AC inductive motor on, it goes from 0 to 60 miles an hour like in 1 second. Boom, bam, it's all on. And I get all this extra torque applied, which does a little bit more damage to my belts and to my couplings. And then I also get that loud expansion noise, the ductwork, and all of that kind of stuff. With the VFD, that's not the case. It starts out ramping up slowly. So it's basically the difference of how I drove my car when I was 16. Right, I would go from stoplight to stoplight. I would just slam the gas pedal to the ground, and just gun it immediately, right? Versus how I drive now, which is like I coast to the stop sign, try to optimize my fuel economy. Then I accelerate slowly, right? I'm a dork that drives a Prius, so you can see the mentality that I have. Right? I'm trying to optimize all of that stuff. And it results in less wear and tear. Like for example, in my car, I didn't replace the brake, the first set of brakes on the front until 90,000 miles. I did the back at 120,000 miles, right? Whereas when I was a kid, dude, brakes every 20,000 miles because I would just beat the hell out of my car, right? The same kind of logic is applying here with the wear and tear. See, Scott has a question. Scott actually has a building where the fans were undersized and they ran the VFDs above 60 hertz. And he's asking if that was bad for the VFD or the fan. I would suspect it probably wasn't good. I don't have any data to support that, and I've never seen anybody run the fan over 60 hertz. But unless the system was designed for that, it might be challenging. We do have some compressors that we run with VFD inverters, and we do overspeed those. So like the compressor I have at my own house has an inverter on it, and it will overspeed beyond 60 hertz. But it was designed for that. So just doing that randomly on a job might be a problem. That's interesting. You actually had a job where the fans were undersized. There's probably a whole story there about how that evolved. When maybe they expanded onto the system, or maybe the ductwork was too small and the fan can move the right amount of CFM, but it couldn't do the static. There's got to be some kind of story there. And Pete chimes in on Scott's comment, asking if the fans were undersized or if there was too much duct leakage in the building. That's also pretty valid. Duct leakage is 25 to 35% for the average system. And that's how much air is getting lost out the duct system and going back into the plenum cavity, which is pretty bad. All right, I'm gonna keep on moving here. So the third fan law is the one that we're interested in for today's discussion. I'll go back to my little laser pointer here. So on this little chart, if you're looking with me here, the fan airflow, the CFM, is over here, or the fan power, versus the RPM. And then on here we have plotted the CFM in orange and the brake horsepower in blue. Now if we look at the third fan law, look at the formula on the left, brake horsepower 1 versus brake horsepower 2. Brake horsepower number 1 correlates to RPM 1, and brake horsepower 2 correlates to RPM 2. So I'm just taking an example here where I change from one RPM to the other. How will that affect my brake horsepower? Well, the brake horsepower, or I should say the RPM, varies in a cubic function relative to the brake horsepower. So what does that mean? Well, that means if I'm cutting this guy back, let's say I'm over here at this RPM of 2. This is not rotations per minute. This is just a quantitative example. If I'm over here at the far right-hand side where it says 2, and I'm operating at that RPM, I'm getting, in this case, this much CFM, but it's costing me that much horsepower to do it. If I cut that guy in half for the RPM, my CFM cuts in half. It goes from this, let's just pretend it's 20,000 and 10,000. It goes from 20,000 CFM down to 10,000 CFM, cuts it in half when I cut the RPM in half. But the brake horsepower went from, in this case, we'll just say it's 8 horsepower, even though that's not what this chart was indicating. It goes from 8 down to 1, right? It goes down to 1/8, which is pretty big, right? So mathematically, if I was to solve that, I guess I should use the numbers that were in the example. That would have been smarter of me. It went from 1,000 RPM. Actually, this example doesn't go with this chart. This chart is separate from the example. 1,000 RPM drops down to 2/3, 677 RPM. My brake horsepower goes from 2 all the way down to 0.6 when I solve that algebraically. So a 33% decrease in the fan speed is a 69% decrease in the energy consumption, which is pretty impressive, and why you'd want to have a VFD controlling your airflow. If you look at all of these things together, we have inlet guide vanes in yellow. I talked about those. We have this VFD speed control in red. We talked about that. We have the discharge damper in green. And the other one we have on here is riding the fan curve. Riding the fan curve means I am lazy and I've done nothing. I have all these dampers out in my zones, and they're throttling back, and I am doing nothing with the fan. I'm just letting the fan just do its thing. So what ends up happening in that case, because the static pressure that the fan is seeing is being increased by the damper shutting, that's causing me to ride back on the fan curve, which is giving me a lower CFM, but it's not really doing a whole lot for my energy savings. It does have a slight energy savings, but it's not really an exciting amount. However, it's more energy savings than the discharge air dampers, which is probably why I've never seen anybody buy discharge air dampers. Inlet guide vanes were the standard, and now VFDs are the standard. Very seldom you see anyone riding the curve, and I've never seen anyone with the discharge air dampers. But you can see the VFD has a significant energy savings compared to the inlet guide vanes as we get to the lower airflows. As I mentioned previously, it's normal to see a VFD running at 40, 50, 60%, and it's not common to see it up at the higher airflows. So in those cases, up here at the higher airflows, it would have been kind of a close discussion of VFD versus guide vane. But when you get down over here below, say, 80 or below 75%, the VFD is kind of smoking the guide vane. He's doing a much better job at the energy reduction, or at the brake horsepower reduction, which correlates to how much energy I got to buy. All right, quiz question number 3. Which can be used to control static pressure on a VAV system? Check all that apply. I'm telling you there's more than one answer. Which can be used to control static pressure on a VAV system? A, inlet guide vanes. B, variable frequency drive. C, bypass damper. D, discharge damper. And I have to press launch because I'm an idiot. Now, there you go. Mallory mentions that on those systems that have the duct leakage, that you can do duct leakage testing to figure out how much there is, and that you can use AeroSeal to reseal it. That's a very good point, Mallory. AeroSeal is excellent. We do it both residentially and commercially on projects. It's an excellent way to seal up, especially existing duct systems that are hard to get back to. All right, I'm going to give you slightly more time on this one because it's a multiple choice one, and I realize in retrospect I shouldn't have picked a multiple choice question, mainly because it just makes it harder for me to grade them later, and I'm lazy. But so be it. Any other questions you guys have for me while we're going along here? We are on slide 17 of 85, so I'm really good at planning. But a lot of the slides are going to go really quick at the end because they're just going to be some examples of different types of VAV boxes and stuff like that. We got one more section to get through of critical things, and then we'll kind of have some fast slides after that. So I'm going to close this poll in 5, 4, 3, 2, 1. The correct answer is actually all of these methods, but when I grade it, if you didn't check bypass damper, I'm going to let that slide because I didn't mention bypass damper to you, and I should have mentioned that as a possible means of doing it. It's just even worse than all the other ways that I mentioned. But it can in fact be done. What a bypass damper does is as the zones throttle back, we have one large damper over back by the air handler, and as the zones throttle back and their static pressure builds up in the duct, we open up that bypass damper and just dump the supply air right back into the return to solve the pressure problem. That would be something you could do. It's dumb, but you could do it. So the correct answers for today are A, B, C, and D, or if you did A, B, and D, that'll also be graded as correct because I didn't explain the bypass damper like I should have. All right, so we're good on fan control, hopefully. Next, we have to talk about compressor control. So the way that I look at compressor control is the same way I look at cooking, which means somebody else can do it. No, I'm just kidding. So in this case, I have this this stove over here, and I have an 8-burner stove, and I'm using 5 of those burners because I have 5 pots on there. Now, I could put the other 3 burners on back over here, but why? There's nothing on there. I don't need that heat. It would be a waste of energy for no reason, and it would just give me extra heat in the room that I don't want. I only need 5 of the 8 burners. I should only use 5 of the 8 burners. My feelings on compressor capacity control are the same way. If I don't need full capacity, why would I run full capacity? I need a way to throttle it back. And VAV systems are all about throttling things back. That's literally what the dampers are doing. They're cutting back capacity. I need to have the fan, which we just took care of, and the compression do the same thing. There's no reason to run all the compression and then have only 1/3 of it be able to be used by the space. It wouldn't make any sense. All right, so if I only need 1 pot of water boiled, I'm only going to put 1 burner on. If I need 8 pots, I'll put 8 burners on. I'm only going to use what I want to use. I'm going to real quick look at the load diversity for Chicago, and if you guys are up in Wisconsin, which some of you are, I apologize that I didn't put up a Milwaukee slide. I just went with the average number of people that are on here today. In any case, this is my loading profile for weather days for the Chicagoland area. And you can see that we have some hours where we're up at 90 degrees, but not a lot of hours. And we have nothing really above 95 and higher. Now, does it ever get above 95? Sure, it does. But statistically, on a 30-year rolling average, it's a very small amount. So that line is so little on here, you can't even really see it. All right, so I don't really care about 95 plus degree days. I'm going to focus on the 91, 92, 88, 80 degrees. I'm going to focus on these days. When I start getting down to these days over here, in the 60s and 50s, those are economizer days. So I don't really care about the compressor much there either. Once they get below 60 degrees, I don't need much compression, if at all. So I'm going to focus more on those. If you can take care of things on a 65, 70, 75, 80, 85 degree day, that is the bulk of the cooling run hours of this compressor. So I want to be able to do that and not so much care about the fully loaded time frame. So that means I don't really need my full compression hardly at all, unless it happens to be 92 degrees outside and everybody shows up to the building. So the ways I can handle my capacity control. I could have one compressor that just turns on and off, very similar to what most of you guys probably have at your house. That's not what I have in my house anymore. I used to have that, and most of us have. But I have one compressor, it turns on and off. And I can cool a space that way. It's not optimal for lots of reasons, including dehumidification, but it's really not going to work on a VAV system. The problem with that on a VAV system is I don't control space temperature like I do at your house or like I do on other constant volume systems. With VAV, I don't control space temperature. I control discharge air temperature to get my 55 degrees. Well, with one compressor turning on and off and my sensor being so close to the results of that compressor, basically my sensor is right at the discharge of the evaporator, if I turn that compressor on, I immediately am going to have like 48 degree air. And I'm going to say, oh crap, turn it off. And then I'm going to have 70 degree air. Oh, turn it on. And like every minute, I'm going to have to turn it on and off to try to get an average of 55 degrees. And it's going to beat the F out of that compressor. In fact, even if I had 2 stages of compression, it's still going to beat the F out of that compressor. You cannot do VAV control with just 2 stages. And if you're forced to do it with 2 stages, you're going to have to do at least some other things to kind of bastardize it a little bit to get it to kind of sort of work. But more stages would be better. So I can put multiple compressors in. I could put in maybe 4 compressors, 6 compressors, 8 compressors. I could do that kind of thing to get more stages of capacity. And I'm showing down here on the bottom kind of a unique way. This is a 2 compressor machine that has 3 stages of cooling, which makes it a little bit unique. So if I had 2 compressors that were not equally sized, let's just say for argument's sake, let's say this is a little small VAV system because that's what this actually was. Let's say I had a 4-ton compressor and a 6-ton compressor, so it's a 10-ton unit. I could turn on compressor 1 and get 4 tons, turn on compressor 2 and get 6 tons, or turn them both on together and get 10 tons, hence my 3 stages of capacity. And then what I could do is use some hot gas reheat to get, or hot gas bypass, excuse me, to add a 4th capacity stage on that. We'll talk about hot gas bypass in a second. But I could get 4 stages essentially that way with 2 compressors. I get 3 actual mechanical stages and then 1 bypass stage. And that would kind of allow me to use a small unit like this on a VAV type system. If we have reciprocating compressors, which you would no longer get on a new air handler or rooftop, or a new condensing unit, I should say, or rooftop, but you might have them on existing ones, and you may want to retrofit them. This is becoming less and less common. This was really popular in the 90s and early 2000s to retrofit these units. But now, if you got a unit that you want to retrofit to VAV and it has recip compressors, it probably means it's a 20-year-old unit or more. So the unit itself is probably ready to be replaced. But if you were in a situation where you want to retrofit recips, the only thing you need to know is that there's 2 types of unloaders you can add. So the way the unloaders work is that unlike a scroll compressor, like these guys, that can only be on and off, and hence the only way I can stage them is by having more of them, a recip compressor can be unloaded. So I can take part of it offline, if you will. I can disable some of the heads on there so they don't really pump any refrigerant for me. So I can unload the compressor. So maybe I might have a recip compressor that has the ability to have 2 unloaders on it. So I could actually get 3 stages out of 1 compressor if I have an unloader on there. And then if I have 2 compressors, each one of them could have 2 unloaders, and I can get more stages that way. I don't need to do that, though. I only need to retrofit 1 compressor. So let's just say I have 1 compressor, and it's got 3 stages, and another one with 3 stages. I only need to put the unloaders on 1 of the compressors. So let's say I'm going to put them on compressor number 1. And then what I can do is I can be smart about how I stage these guys. So I can get a lot of stages this way, right? I can have stage 1 turn on, stage 2, put all of it on for stage 3. Then when I want stage 4, I can stop using compressor number 1. I can turn on compressor number 2 in its entirety, and then just keep compressor number 1 loaded over here. So I can have the second compressor on, so stages 4, 5, and 6 would be on along with 1. And then 4, 5, and 6 with 1 and 2, and then all 6 of these could be on. I can get 6 stages by putting 2 unloaders on the lead compressor and having a smart control sequence. But the thing I want you to know from this discussion, in case you ever retrofit one of these, is there's 2 types of unloaders that can be put on a recip: pressure unloader and electric unloader. You have to use electric unloaders. I will repeat, you have to use electric unloaders on a VAV system. The pressure unloaders do not react quick enough. Pressure unloaders can only be used on constant volume systems with recip compressors, because in those cases, the compressor is staged based on space temperature, which is slow to react because the air has to come into space, mix, and then make its way to the thermostat. VAV systems are controlled by discharge air temperature, which means the sensor that is in control is going to see the effects of the compressor turning on very quickly, because the discharge air will change much quicker than the space temperature will change. And if I put pressure unloaders on there, those pressure unloaders have to wait until the refrigerant pressure gets to a certain point because of the way my evaporator has been loaded by the actual load conditions, and then it'll unload. But I need to unload it faster than that, and the pressure unloaders are too slow. You cannot put pressure unloaders on a VAV system. Do not even try to do it. It will never, ever, ever, ever work. You have to use electric unloaders, which means my DDC controller that controls my VAV system will be the one controlling the unloader directly. You can do what's called hot gas bypass. Now, this is not an official stage of compression, even though it's kind of like having a cheater stage. And as far as the energy code is concerned, which we'll talk about later on, it does not count as a stage of compression, but you may still want to do it. So you may have a system that's kind of small in tonnage and you can't get 6 compressors or whatever. It only comes in a 3 compressor version. You may want hot gas bypass on the lead compressor of a 3 compressor machine. So it kind of gets me a 4th stage. So I can take 1 compressor offline. I can take 2 compressors offline. And now I have just that 1 lead compressor running by himself. But if that's too much capacity, I can do the hot gas bypass mode. So in the simplest form, what does that mean? It means I'm going to take some of the hot gas off the compressor, and instead of sending that hot gas out to the condenser for that heat to be rejected outside, I'm going to take it and I'm going to shove it back into the evaporator to falsely load the evaporator. So I don't satisfy the space needs as quickly, or in this case, the discharge air temperature needs as quickly. I'm taking hot gas and I'm dumping it back into the evaporator and mixing it with my cool refrigerant. So my evaporator temperature is going to actually be elevated. I'm falsely loading the compressor for no reason other than I don't want to shut the machine off. It still allows me to get some dehumidification. It still allows me to get some cooling capacity into the space, but it is not efficient by any means. But I will put this on the lead compressor if need be. You can also do what's called a RAL device. That is a specific manufacturer of hot gas bypass. The guys at RAL will say that they're not hot gas bypass. They are different. They do it differently, and they do, in fact, do it differently. But when push comes to shove, I'm still, at some point, going to be taking hot gas and letting it skip the condenser and putting it back to the evaporator at some point. So it's a form of hot gas bypass, if you will, but it's a better form. In either case, hot gas bypass is not efficient. It's less efficient than anything else you could do with compression. It's just a necessary evil, especially when I have scroll compressors nowadays instead of recips. It's a necessary evil to get those lower stages on. The next thing I could do instead of hot gas bypass is I could get a digital scroll. So what's a digital scroll? It's a way to modulate a compressor capacity. So I may, once again, have 3 scroll compressors, and on the lead scroll, I'm going to make it a digital scroll. So I shut off compressor 3, I shut off compressor 2 because I have too much capacity. Now compressor 1 is on, it's still too much capacity. I'm still dropping below my 55-degree discharge air. Now instead of turning that compressor off and having no cooling, I can start modulating this compressor down. This compressor is kind of unique in the way that it works. I believe Copeland is the only manufacturer of these, but they get used in all kinds of brands of equipment. And the way this guy unloads is he basically disables the scroll temporarily. Let me see if I can get to, see here. My mouse thing is not working. Oh, there we go. Oh, come on, do that. I should have a better drawing of a scroll, but I don't. But if you look at the top of a scroll, that crappy drawing is what it would look like on the bottom of the scroll. And then the top of the scroll would fit in with that the opposite way. So this part up here in the compressor, it has the bottom scroll I just drew here in yellow, and then the top scroll in orange. And that scroll kind of swirls together, and that when the refrigerant enters there, as it swirls around, it's getting a smaller and smaller passageway until it gets into the really, really small end where it gets smashed out, right? Compressed out and ejects out the top here. But what happens in a digital scroll is, if you can envision this orange part I'm showing down here on the bottom, it physically lifts up out of the yellow part. It's still spinning, but it's no longer connected with the other one. So it's no longer compressing refrigerant, and the refrigerant is just essentially bypassing it. So the way the staging works on that is, if it keeps them together, that compressor is fully on. And then it can separate them. Let's say it separates them for 5 seconds and puts them together for 5 seconds. Separates for 5 seconds, puts them together for 5 seconds. Well, that's 50% capacity. But it could also separate them for 8 seconds and put them together for 2 seconds, right? And now it's going to be 20% capacity. So it can pulse how long it keeps them apart to get the amount of BTUs that I happen to want to get out of that thing. And we can have a whole separate class on just the digital scrolls. The other thing that can be done is a inverter-driven variable speed compressor. So this is what you would see like on a VRF type system, or this is what I have at my house. The inverter on the left side of the picture there is actually the inverter that I have at my house. I actually have a smaller version of that inverter. It looks kind of like that. So with these variable speed controls, they can be put on many types of compressors. The digital scroll, based on the name of it alone, only goes on a scroll compressor. But I can put an inverter, essentially a VFD, if you will, on just about any type of compressor. Ductless mini split guys do it a lot on the scrolls and rotaries. Residentially at my house, I have a ducted system, traditional ducted system that has an inverter on a rotary. In the lab over here, I have an inverter on a scroll. Obviously put in VFD inverters on large centrifugal chillers. Lots of things you can do with that. But I could throttle back the capacity of the compressor that way. It uses less energy than a digital scroll. It's more efficient, if you will. Although the digital scroll is pretty good, it's much more efficient than hot gas bypass for sure, as the chart was showing on this page. But an inverter would be even a little bit more energy savings. Not dramatic, but a little bit more. It doesn't usually have as good of a turn down as the digital scroll. In this case, these inverters can drive down to 20%. The digital scroll can go down to 10%. I don't know if that's a big deal or not, but that's a little bit of a slight difference there. Long story short, I got to have a way to control the capacity. I cannot have 1 or 2 stage units put on a VAV system. And even 3 stages is pushing my luck. If it's 3 stages plus hot gas bypass, okay, you could probably do that. But anything less than that is probably going to be difficult to control discharge air, especially if the unit is oversized, which most of them are. Some rules of thumb here. VAV systems, by definition, are cooling only. You can force them to go into a heating mode. Many of them, especially rooftop units, have something called occupied heat, and you can force the unit to go into the heating mode. But when you do that, you should know the normal sequence of operation for occupied heat is to go back into morning warm-up. A morning warm-up sequence of operation is force all the dampers in the system wide open to 100%, ramp the fan up, and turn all stages of heating on and blast the space. That's what happens for morning warm-up. That's what happens for rooftop occupied heating. So you're normally not going to want to do that. Now there's the tempering thing that Ben asked about earlier, and that's a different discussion. But normal heating, for purpose of heating the space, don't try to do it with the air handler. It's not going to work at all. I've never had a job that worked that way. Let's take that back. If I didn't put one VAV air handler on the whole floor, like I showed you in my other drawing, my floor plan drawing, and instead I put a small VAV unit on the east, another one on the west, and one on the south, and one in the core, if I kind of divided it up like that, put 4 small VAV air handlers in, then I could get away with it. I could actually do it. Because then I wouldn't have zones that wanted opposite things at the same time. I wouldn't want somebody that wanted heat while somebody else wanted cooling. So I can get away with it if I did it that way. But if I had one floor laid out, it's not going to work very well. How am I going to go and give you 100 and some degree discharge air temperature when for the perimeter zones when the interior zones want 55-degree cooling? As Ben pointed out, if I have a lot of outside air requirements, I may use modulating heat or staged gas heat, which is a separate thing you would have to pre-plan and buy and order that way from a controls and equipment standpoint. I might use that to bring the temperature back up to 55 or maybe even up to 60 degrees because I could probably figure, yeah, you know what, my interior zones can get away with 60 if I needed to in order to make life easier on my perimeter zones. But I definitely can't shove 80 degrees into those interior zones. If you need heat, which you will need heat for the perimeter, you need to have local heat, either baseboard or ducted heat, but you got to do that. If you choose to heat from overhead, meaning you're going to put heaters on the VAV boxes and you have a supply duct that goes overhead, there are several rules that come into play, both in the ASHRAE handbook and in ASHRAE 62, which is the indoor air quality standard. You have to throw air towards and away from the glass. You got to make the air, you got to choose the air diffusers at a point at which they are able to throw the air 50% of the way down the glass window. And you need a maximum of 15 degrees above the space temperature. I said on my slide here 90 degrees, figuring maybe you might heat the space to 75, which is kind of hot. But if you heated the space to 75, the hottest supplier temperature you could have would be 90 degrees. If you have air temperature that's hotter than 15 degrees above the space, the air will definitely stay stratified and hug the ceiling, which means you will not heat the space, you will heat the ceiling. And then eventually you'll have enough heat at the ceiling that it'll push its way down into the space. And the thermostat will get satisfied because he'll get the temperature that he wants because the thermostat always gets what he wants. But you'll have 130 degree air at the ceiling and you'll have 52 degree air at the floor, and people will complain that they're cold even though their thermostat's at 74. They're cold because their feet are cold. If you keep the air temperature lower and you only provide 80 or 85 degree discharge air, that allows the air to be thrown down towards the floor from the diffuser like it's designed to be done. And then I get better mixing in the space and I have more equal air temperature and less stratification. So keep that in mind if you're doing overhead heating. It's especially critical on VAV systems because of the turn down on the boxes. You got to have modulating cooling like I mentioned before. It cannot be 1 or 2 stages. You got to have lots of stages, or you have to have some kind of modulating compression in order to control supplier temperature. You have to have variable capacity fan control, probably going to be a VFD. There's no reason to do anything other than a VFD at this point. So you got to have that. So a VAV air handler has to have modulating cooling and a modulating fan. If you only have one of those two things, you don't have VAV. You have a hybrid, and we'll talk about hybrids next week for those that are interested. You have to have some way of variable exhaust systems. As my outdoor air damper modulates and my fan speed that's sucking air through my outdoor air modulates, it is going to change the pressure in the building. I need to have something that measures building static pressure and then either ramps up and ramps down exhaust fans or stages up and stages down small exhaust fans, one or the other. Do not put the building static pressure sensor in the lobby area. It'll see too much effect of the doors opening constantly on a fairly busy building. So put it somewhere in one of the general hallways. So if you got a 3-story building, put it in the first floor in the hallway away from the lobby doors, something like that. You can choose to poke the pneumatic tube for the sensor through the ceiling tiles, or you can buy like a $2 wall plate that's like the size of a light switch plate and put it on that. That's the way to go. If you put it on the ceiling tiles, eventually somebody's going to move the ceiling tile for some reason or another, and it's going to jack up your tube. So putting out a wall plate on the wall keeps it out from being messed with, if you will. Quentin asks about, is there any code requirements for VAV static pressure set point and location? There is, and we're going to get to that in about 5 minutes. Quiz question number 4. Which is not, I repeat, which is not an acceptable compressor capacity control for a VAV system? Your choices are going to be 2 inverter compressors, 1 digital scroll with 1 fixed speed compressor, 2 scroll compressors with hot gas bypass, or 4 scroll compressors. Which one would be not a good idea to put on a VAV system? Some of them are obviously better than others, but one of them is really bad. Okay. All right, I'm going to give you guys like 8 more seconds because I'm going to try to pick up my pace and get my other 80 slides done in like 7 minutes. There was one time I did a class where I didn't prepare enough material. It was back in 1997. So now I always have double the amount of material that's needed. All right, 5, 4, 3, 2, 1. I realized just right now that I wrote this question, so all 4 of the answers are actually acceptable answers. I forgot to put option E on there, which was going to be 2 scroll compressors. So I did not actually put a bad option on there. C is probably the worst option, 2 compressors with a hot gas bypass, but it's kind of decent. A is good, 2 inverters is good. B is good, 1 digital with a fixed speed is good. 4 scrolls would be good. C would be the worst answer, but I didn't give you an actual truly bad answer. So everyone gets everything right apparently. That was an easy test. All right, I'm gonna power through a couple of these here. The energy savings comes back from the diversity credit. You buy smaller equipment, the equipment costs less up front. It makes it easier to have load control if you don't have all those extra capacity stages that are never needed. So do not put in a system that's a size for 100% of all the zones added together. It's going to be smaller. Your equipment's going to be smaller. The energy savings comes off the VFD like we discussed. There's some things that we can do that are helping us from a control standpoint, a comfort standpoint, and an energy code compliance standpoint. Supplier temperature reset is one of those things. If you have DDC controls, then this is required by the International Energy Conservation Code, both the version we use in Wisconsin and the version in Illinois. You have to do supplier reset if you have DDC. If you don't have DDC, you don't have to do it because it's pretty much impossible to do this on pneumatics. But all that really means is we look at all of the zones, and if all the zone temperatures, as an average, are cooler than the set points that they want, then as an average, we're overcooling the space. So what we do is we increase the supplier temperature from 55 up to 56 degrees, or 58 degrees, or 57.2 degrees, or whatever our controller calculates. And we set it up slightly, and that way those zones don't need quite as much of that reheat on the perimeter that they might have otherwise need. We help the zones out that are getting a little bit overcooled by the 55, and we reduce some of the extra heating capacity needed for the reheat. Now you're kind of limited. The code requires you to do it up from 50. If you have a 55 degree set point, the code requires you to do it to 60 degrees. You have to do it 25% of the difference between the supplier and the space temperature. If I assume 75 degrees in the space, which the code also requires, that means I have a 20 degree delta. 25% of 20 degrees is 5 degrees. So if I use all the code numbers and I have a 55 degree design temperature, I have to reset it from 55 to 60. You could probably push your luck and reset up to 62, but at some point it becomes difficult to cool the interior zones. So you can't really go much higher than that. We can do what's called static pressure reset. So what this does is we look at all, and once again, you're only going to do this if you have DDC controls. We look at all of the zones to see which zone is the worst, meaning who's the most open, which guy's calling for the most amount of airflow. And if nobody wants 100% of their airflow, well, then I must be giving you guys too much air. I'm just going to give you less. So if the most open zone is 80%, well, you know what I'm going to do? I'm going to change the static pressure set point from 1.2 inches of static to 1.1 inches of static. And I am going to give you less airflow, right? And I'm going to keep dropping it down lower and lower and lower on the static pressure set point, which lowers my VFD, which lowers my CFM. I'm going to keep lowering that until somebody, one of the dampers, gets back to requesting 100% airflow. And when he wants 100% airflow, obviously I'm not able to give you anything more. Your damper's wide open. I'm going to have to raise the static pressure set point to give you more CFM at that point. It's pretty easy to do. Both supplier reset and static pressure reset are easy to do with DDC controls. It is a standard control function that every DDC manufacturer can do. It's not proprietary, but you need to ask for it up front. If you build the building, set up the controls, and everybody's done with the job, and then you ask the controls guy for that, it's going to be an extra. If you ask for it at bid time, it'll cost nothing. It'll be free because it's just a matter of just doing it slightly different when he sets it up. So make sure you ask for that. It will not be a cost penalty in your open bid process. And then we can also demand control ventilation on these systems. That's a whole other topic in and of itself. but that can be applied to VAV. It's a little bit different. I do need to have CO2 sensors on each damper, or at least on the dampers that are most representative. And then I can use an equation from the ASHRAE 62 called equation 6.1 to mathematically calculate the other zones. I never ever do it that way. I always put one sensor on per damper. It is by far the easiest way to do that. Types of VAV boxes. I wasn't going to go into these in really long detail. I am going to save that for another day, and I'm just going to talk about these generically for you right now. And we'll save VAV boxes for a separate topic in July for those that are interested. But the ones that you're going to see most often are going to be single duct VAV boxes, which just means it's just a damper. Typically, it's a round inlet and a rectangular outlet. The inlet is smaller than the outlet because in addition to having a damper in there to throttle airflow more or less, it also has a job function of converting the duct static pressure system from a medium pressure system to a low pressure system. So on the inlet of the box and the main supply trunk, it's typically historically been medium classification ductwork, and on the discharge side has been low. Although a lot of times now we're doing both sides of the box as a low pressure system. That's the most common VAV box that you would have. The other two common types that you have are going to be parallel fan power boxes and series fan power boxes. And those guys are going to be able to, see if I can get you a picture of that without going too deep in here. I'm going to skip a few of these in the interest of time. It's a whole other day. All right. Let's do it this way. A series fan power box means there's a fan in the box in the terminal, and the fan is in series with the inlet from the air handler. So here's my 55-degree pressurized air coming from my air handler, and all of that air must run through this fan. As this damper throttles back, that means this fan's going to get some of its air through this induction plenum, this opening over here. He's going to pull air in from the plenum itself. So then he's going to have 55-degree supply air here, and he's going to have 78-degree plenum air over here, and he's going to mix the two of those. This fan's always going to provide constant CFM all the time. And he'll just have this damper being throttled more or less. As compared to a parallel box, I'll pull up a drawing of that real quick. A parallel box, the fan is not in series with the damper. It's obviously in parallel. So the 55-degree cool air comes from here, and then my plenum air can come from here. This fan is not running all the time. This fan only turns on with a call for heat. So it would be the first stage of heat is to turn this fan on and try to bring in this 70-some degree plenum air to heat my space. And then if I still need more heat in the call for second stage, then turn on my duct heater or whatever else I have. There's the argument between parallel and series. It's just mainly a preference thing for the designer. The benefits of series are there's no noise of the fan clicking on and off. Since the fan always runs, it's a constant noise. Whereas sometimes on a parallel job, we do get some complaints from the occupants that they can hear this thing clicking and turning on. So that is one factor of it. The other factor is if I have a parallel box, then my air handler fan has to be sized to get the air all the way to this damper, through the box, through all the rest of the ductwork, and through the diffusers. If I have a series fan, the air handler fan only has to be sized to get the air to the box, and the series fan does it the rest of the way. All right, let me skip to the very last thing here. I'm gonna skip a whole bunch of stuff, and like I said, I'll do a VAV damper discussion with you guys on another day. I apologize. I was super optimistic about how much stuff we could cover. All right, let me just take 5 minutes to cover the code stuff and pop up the last quiz question, which relates to the code stuff, and then we'll be wrapped up. So this is for the 2018 code. So this is for the Illinois guys. It also does apply in Wisconsin. It's slightly different on how it's worded in 2015, but as far as a VAV system goes, it'll be the same result. Constant volume, the answer will be different for the two states. VAV, the answer is the same. So if I have units that control space temperature by modulating airflow to the space, in other words, I have dampers on the zones, in those cases, I have to have a modulating fan speed control, as it says down over here in note number 2. Not a big deal because I probably would have put modulating fan speed control on the VAV air handler anyway. So we're good in that regard. The one that's going to be a little bit more thought process and work is that when I have a system with an economizer, which is going to be anything that is 5 tons or greater is going to have an economizer. If I have a system with an economizer, specifically an air side economizer, water side economizer, different rules, but I have an air side economizer, then I'm going to have these rules that kick in over here, specifically rule number 3. If I am controlling space temperature by modulating airflow to the space, which obviously a VAV system is, it's a space thermostat, temperature sensor, that is controlling a damper that controls airflow. That is what that is. I don't know why they couldn't just say for VAV units, this is what you got to do, but they worded it in that funky way. In those scenarios, if I am between 65 and 240,000 BTUs, which would be between, between 6 tons and 20 tons, then I have to have 3 stages of mechanical cooling, and it specifically states that hot gas bypass does not count as a stage. So I have to have 3 compressors, or I have to have 2 compressors unequally sized with a sequence of operation that operates them in that 4, 6, and 10 ton discussion that I had earlier, or I got to have a digital scroll, or I got to have an inverter on there. And then if I get above 20 tons, I got to do the same thing with 4 stages. I got to have all those extra stages if it's going to be an air dampered system. Hot gas bypass is limited, as I mentioned before, based on the code. So you can use it, but it cannot count as one of your mechanical stages of cooling, and you can't use it for more than 50 or 25% of the total capacity, depending on the size of the system. All right, the question before that that someone had typed in, I believe it was Quentin. This is new for the 2018 code, so this applies to Illinois, but not to Wisconsin. The static pressure sensor must be located in whatever location it needs to be in order for the set point of the VFD to be 1.2 inches of static or less. A lot of VAV systems were historically set up for 1.5 or 2 inches of static, and then we threw the sensor 2/3 down the duct and called it a day. So now you're going to have to put it somewhere further downstream than you would have with 2/3 in most cases, and wherever it needs to be 1.2 inches. This does save energy, but more importantly, the reason that this is on here is to make it easier for the inspector to police. It's pretty easy to go up to the VFD control or the automation system and see if it's set for 1.2 inches or not. But that's where that sensor has to be. It has to be wherever it needs to be 1.2 inches of static or less. That's the location you have to put it in. So you can no longer do 2/3 of the duct. You definitely can't do it at the discharge of the fan. 1.2 inches wherever that location is. As I mentioned, you have to do the duct static pressure static reset. I talked about before, that's a requirement. You have to do the supply air temperature reset. That's a requirement by the code, as I mentioned before as well. That's both the 2018 and 2015, so Illinois and Indiana. And actually, so both those are Illinois and Indiana. As is the fractional horsepower. If you have a series fan-powered box, the 2015 and 18 codes will require you to put an ECM motor on the series fan-powered box. You will not be able to achieve the requirements of this code spec if you put a PSC blower on there. It's got to be an ECM. Now, if you have a parallel box, you could still use a PSC blower if you wanted to, because in those cases, you'll be in the exception category of number 1 right here, where I'm only using the fan to provide heat to the space. So a parallel box does not have to have an ECM. A series box does have to have an ECM. And then the last thing that relates to code, and we'll be all wrapped up here, is that in the 2015, it would have been 30%. The 2018 code is 20%. So what this is telling you is that you have to throttle the damper back to 20% of its cooling design before you can even begin to engage the heating of the VAV box, right? So all those zones have supplemental heat, especially on the perimeter. Before I'm allowed to turn the heater on, I have to throttle the damper back to 20%. So I got to provide less and less and less and less and less and less cooling until I get down to 20%. Then I can still go lower if I want to, but at 20%, then I'm allowed to start engaging the heat if I need be. All right, last quiz question. Actually, there's 2. I'll do them right now. Per the IECC 2018, where must the duct static pressure sensor be located? 2/3 down the duct, in a location that allows for a set point of 1.2 inches or less, at the fan discharge, or at the farthest VAV box. We'll answer this one. I'll pop up one more quick one, and then we'll be done. Anybody have any other questions for me? Once again, I apologize for not being able to go through all the gory details of the actual air terminal boxes. I will schedule a day to do that as another separate webinar since I wasn't fast enough today. All right, 80% of you have answered the quiz question, so I will give you 5 seconds, 3 seconds. And the correct answer is, in fact, B, wherever it needs to be 2/3 of the way down the duct. All right, the last question is, there's no right or wrong answers. It's just to prove that you made it all the way to the end so I can give you your hours. How do you rate this overall webinar? So let me read some questions from you guys if there's any more here. Chun asks why the control circuit is 24 volts instead of 120, 240, 480. That is not just specific to VAV. We do that for almost all systems, rooftops, air handlers, chillers, VRF, everything is running on low voltage controls. And there are numerous reasons for that, but the main reason is that it makes it easy to run the wiring cables around the building, because in most places, 24 volts does not need to be in conduit, whereas 120 and up would definitely have to be in conduit. Now, there's some exceptions to that. For example, in the city of Chicago, in a plenum cavity, you would have to put 24 volts even in conduit for 24 volts. But most places you can run 24 volts without having to be in conduit. And then having wires run around the building not only is not being conduit, which means it doesn't cost as much, it's also safer to have lower voltage stuff around the building. Not that 120 is not safe, because obviously you have 120 at your light switch, but it's just easier to have that open cable running to the plenums like that. There's very few things that don't have 24 volts for controls anymore. Typically, industrial type heating things, like an electric heater, or maybe like a gas unit heater in a warehouse, those might have 120 volt thermostats, line voltage thermostats, but almost everything else is 24 volts these days. Matthew asks, how can you comply with 62.1 for minimum space ventilation if you have to set the VAV minimum for 20%? All right, so there's a couple answers to that. He's referring to this part of the code here. So the first thing that I would answer, not picking on Matthew, but just people in general, is that lots of stuff is oversized. Lots of stuff. So if I put in a smaller damper, it's going to be a lot of scenarios where I'm over this 20%. So if I get things correctly sized, this problem comes up a little bit more than you might expect. If I read some of these exceptions, I believe one of them is going to help me out here. Shall use the volume following. I thought one of these was an exception. Okay, no, up in the next column, number 3. The outdoor airflow rate required to meet the minimum ventilation requirement of Chapter 4 of the International Mechanical Code. And as you probably know, the IMC is same tables as ASHRAE 62.1. So it's telling you have to do all of these things, 1, 2, 3, 4, 5 of these guys here. And you have to go down to these minimums. So you have to reduce the volume of air to these minimums to one of these following. And one of the minimums you can choose to operate at is the outdoor airflow rate minimum. So if, say, let's say your particular zone needed 28% airflow at this moment, I could put it at 28% airflow because that still meets number 3 of my rules. So hence I don't have to do number 1. I only have to meet one of these at any given time. You know what I'm saying? So I have to reduce the amount of airflow in each zone to one of the following. I could pick and choose 1, 2, 3, 4, and 5 and do any one of those at any given moment of time. Oh, sorry, I still had the quiz thing popped up. All right, so with the way the code language is, you have to do one of the following of these. Number 1, number 2, number 3, number 4, number 5. And you can do as the moment changes, you can pick which one you're doing. So your control system can switch between these things. But if I modulate down to the minimum airflow required per the mechanical code, then I don't have to do number 1 because I'm in fact doing number 3 instead. Let's see. Ferris says some ductwork is exposed to the outdoor. Can those VAV boxes be designed and used for like you want to mount the VAV box outside? Typically, no. The VAV box, generally speaking, will not be able to go outside. It's not impossible to do that, but you would have to buy a VAV box and put like a NEMA 4 enclosure on it or something like that to put the controller inside there. At that point, it would just be easier to put it inside. So you could get it outside if you absolutely had to. Now, a lot of electronics, some electronics are for outdoor use and some are not. So for example, the circuit boards that we use in our packaged rooftop units the circuit board itself has like an epoxy coating on it, which makes it more resistant to like humidity and stuff like that. Whereas the ones that are used in most VAV controllers probably don't have that because they weren't really designed to go outside. The temperature wouldn't be that big of an issue. If the enclosure was small enough, you probably get enough heat off of the circuit board to keep it decent temperature in there. But the humidity probably would become an issue. And if you made the controller tight, if you made the enclosure tight enough, then you probably have a problem with heat and the rest of the year. So just don't put it outside. Keep the VAV box controller inside. It'd be much simpler to do. What other questions? Anybody else? All right, well, I don't see any other questions. And I already went 17 minutes over my allotted time, so I apologize for that. As a reminder, for those of you that were doing this to get PDH hours, you'll get a certificate auto-emailed to you from GoToWebinar today. That will not be the PDH certificate. I'll get the quizzes graded, and Kelly will send those out in a week or two once she's able to get them all typed up. So you get a second certificate later that specifically spells out the PDHs. All right, well, thank you guys for your time. Appreciate it.